Hi there. Here's a case study related to building science that I hope you find interesting and informative. The idea of these case studies is basically to bring together some of the concepts that you've been learning and see them illustrated through an actual case. And so the case that I'm going to talk to you about today begins with this building that you see before you. It's a concrete block and brick storage building located about 3/4 of an hour north of Toronto. And it was built 3 years before we actually saw it. And it worked well for 3 years. But in year 3, in the wintertime, in January, the owner noticed that the first floor partition walls began to buckle. And so they called us and they tried to fix it. And the buckling actually continued. And so what was causing the buckling? And we were asked to investigate. And the interesting thing is that there were several theories about how it happened. One of the theories was structural settlement. Well, we had to go and look and do our investigation. And so we're going to talk a bit about what we actually observed, what we thought about, what are possible causes, what was the most likely cause, and then what the solutions are. Okay, here I am with the light board, and what I'd like to do now is talk a little bit about the observations that we made when we looked at the site. The first thing I want you to notice is when you look at the photograph of this building, it's a solid masonry building, and it has basically perimeter walls and interior load-bearing walls, but it's a storage unit. And the storage unit's basically made up of a whole bunch of partition walls. And the first point here on observations, if you look at this building in the photograph, you won't see any cracks in the masonry. It's brick and block, and there are no cracks. The second thing you'll notice is that this is building number 7, and we were asked to look at building number 7. Buildings 1 through 6 didn't have any problems. It was only building 7 that had problems. So what about building 7? Well, we went inside, and when we went inside, you can see it here in the photograph, the first floor partition walls buckled. And I've done a little drawing here to show you the buckling of the partition walls, but these are the steel stud walls and gypsum that basically are the demising walls that divide up the storage units. And those walls, and you can see it in the photograph, those walls have actually buckled. Not only that, they buckled after they were fixed. It was early January when they first started buckling, and by the end of January they'd fixed them, and when we went and looked at it, the building was still buckling. So there are forces still at work here, and you can see it in that photograph. The next observation is that the temperature outside on the day that we were looking at the storage units was minus 10 degrees Celsius. And in fact, when we took a slab temperature, the top of the first floor concrete slab here was minus 5 degrees C. So although the building might have been heated, and there were some heaters, and you can see them in that photograph, there are small heaters, and there's a question whether or not they were turned on. The other thing to notice about this storage unit is when we went in, it was vacant. Nobody had stored any stuff inside. Buildings 1 through 6 were being occupied. We weren't allowed to see them, but the number 7 building, it was unoccupied, probably unheated, and you'll also see a ventilation fan. It was ventilated, perhaps in the winter, perhaps in the summer only. I don't know, but what we do know is it's a large leakage opening. And the last observation that we made when we were on the site is the first floor concrete floor slab. It basically cracked. So this slab here, here's the concrete slab, it cracked. And here's the masonry, here's the roof, an internal masonry wall. And I'll just draw how this foundation goes. This goes right down to the foundation. And the foundations were 1.6 meters below grade. And same over here. So with those facts, the question became, how is it that these steel studs here on the first floor, and only the first floor, the partition walls on the second floor, they didn't buckle. These are non-load-bearing steel stud walls, and they're buckling. What was creating the force? Well, one of the theories that was put forward was that the whole building was settling. And at the very beginning, I told you that this was a building that was 3 years old. It was 3 years old and it's January and suddenly it starts settling? How come it didn't settle in years 1 and 2? And the next thing is, if this whole building is settling and it's going down, if the building is truly going down like this, because this is settling into the soil, how come there's no cracks in the masonry? Because remember I said there were no cracks in the masonry. We looked on the inside, we looked on the outside, no cracks in the masonry. So it's probably not structural, it's probably not settlement that's creating this. So what could be doing it? What I'd like you to do now is pause the video and think, is there something other than settlement that might be causing these non-load bearing walls to buckle? I'd like you to think about that. So have you thought about another theory that might explain what we've just observed? Remember, it's year 3 that the problems occur with the buckling studs. And it's in January. And it's probably not settlement. So what else could it be? If it's not the building going down, could it be this first floor slab going up? Is there something that could cause that slab to go up? And the answer is yes, there is. This building, and I told you it was north of Toronto, is in a city that's famous for silt. And silt is one of those materials, it's a soil that's frost susceptible. Is it possible that frost got into this underneath these floor slab and caused it to heave up? Well, when we looked at the drawings called for about 300 millimeters of granular A. It's a free draining gravel material that's not frost susceptible. The problem is, down here, we know from experience in the city that it's probably silt, and silt is frost susceptible. So could frost be used to explain all these things? Well, for frost to occur, we need 3 things. We need freezing temperatures. We've got freezing temperatures. In the silt, perhaps it penetrated that far down in the freezing. We also need a source of water. Well, the wonderful thing about water is it's always down here. There's a water table here, and silt exhibits capillarity. So water actually wicks up. And so it's possible that water can wick up to feed what we call an ice lens. And I'll draw this for you over here in a second. We get ice lenses. These ice lenses in freezing soil form basically and cause heave in the direction of heat flow. And if the subgrade is cooling, it's cooling, the direction of heave will be up. So is it possible that frost actually pushed this slab up? Well, I said we needed 3 things. We needed a frost susceptible soil, silt we've got, we need a source of water, and we need freezing temperatures. We've got all of those things, we think. So is frost pushing it up? Is it consistent with all the observations? No cracking of the masonry. Well, the freezing line's above the depth of frost penetration. Because in fact, what we've got here, right here, this is the freezing line, the foundation is actually below that freezing zone. So it's not being heaved up, just the slab's being heaved up. Only building 7. I'll leave that one for a minute. The first floor partition walls only buckle. That's consistent because these didn't buckle. This is just pushing up against the floor slab. So that's consistent. Our slab temperature -5, it could cool the subgrade, yes. Heated and ventilated, we don't know if the building was heated, probably not given the slab temperature. And the first floor concrete cracked. Well, that's consistent with the slab actually being heaved up. So all of these pieces fit the puzzle. So why was it only building 7? And like any problem, you never have enough money, you never have enough time to do a complete investigation. We're just estimating, taking our best guess, that it is silt, but chances are it is a frost-susceptible soil. And we don't have a soils report, but we know that this particular winter, it was about 15% colder. The heating degree days were 15% more than in the normal period. So it's possible that it got below the depth here. But why, and that's the question, why only building 7? And perhaps the answer is, in the other buildings, there was stuff. And that stuff actually insulated the floor. And it kept the heat in the soil so it didn't freeze. It's our theory, and everything else is basically consistent with frost. So where to from here? Well, now we have to think about how do we fix it. Okay, now it's time to think about solutions. How can we address the problem? Well, if we're designing it from first and it hadn't been constructed, there are a couple things we could do. First of all, we could put more granular material in here, because if we'd put in granular material to the depth of maximum frost penetration, we would have been fine. So remove the silt. Remember I said there are 3 things we need for frost heave? Freezing temperatures, source of water, and a susceptible soil. If we put in a free draining granular material, non-frost susceptible, but that costs a lot of money, you have to remove it. In this case, they only put in 300 millimeters. But if we went down, say, 1.4 meters, it would be better. Another solution is actually, instead of putting in all that granular material, is actually right across here. And I'm just going to use the magic eraser here. Right across here, let's put in some insulation. And that insulation is extruded polystyrene foam insulation. And if I was designing it from first principles, and it hadn't already been built, just guessing here, north of Toronto, about 50 millimeters of extruded polystyrene foam insulation underneath the slab will keep the silt down here in the subgrade from freezing. We still use some granular material, but now I'm just going to insulate the soil. So that's another solution. Okay, or I could just heat the building. The problem with heating the building is that costs money and it costs the environment. So what are we going to do with the existing building? Because I can't put insulation underneath the slab unless I rip out the slab. I don't want to do that. But could I put the insulation on top of the slab? And that's a possibility. The only problem with that approach is all your transitions, all your doorways, everything else has to be redone. But in the end, you could heat it, you could insulate it, or you could put in free draining granular material. All of the above, any one of those solutions would work. It's a matter of finding which one's the most cost effective and have a mind for what's the best for the environment.